Hello. So, today we will discuss the discrete Fourier transforms and an efficient algorithm to compute these. Many of you might have seen Fourier transforms of functions. In case of discrete Fourier transform, we will be computing a transform of a vector which you can think of as a function with n values. So, what we have here is a ring where R is a set and which has got two binary operations, the plus and multiplication. It has two special elements in it, so called 0 and 1. This is a ring in which multiplication is commutative. So, it is a commutative ring with a unit element. Other properties we have earlier discussed are the same, namely with plus R is a group, which means for every element there is an inverse. So, you can have A and there is an negative A such that their sum is 0, A plus 0 is 0. With multiplication, one plays the role of identity. So, A times 1 is A, 1 times A is A because it is commutative. By commutative we mean A times B is equal to B times A, and multiplication distributes over plus, which means A times B plus C is A times B plus A times C. This holds. Now, given a vector on this ring, so components of the vector belong to this ring. So, I have an n vector A0, A1, an minus 1. Its discrete Fourier transform is a vector B0, B1, Bn minus 1. There are many useful properties this transform has, and it helps us compute certain quantities which are difficult to directly compute in terms of complexity. So, we will first formally describe the Fourier transform and later on we will deduce certain properties and describe an algorithm to compute the DFT, which is discrete Fourier transform, more efficiently. So, let us try to describe the properties. We need the ring, the requirements are first that n has a multiplicative inverse. That is, there exists M in the ring such that n times M is 1. This in general is not necessarily available in the ring such as this. 2, we also need that there exists a primitive nth root of unity of 1 call it omega. What this means is that, well, I will just write down that W or omega power n is 1, which makes it an nth root of unity, and omega power k is not 1 for all k between 0 and n. Okay. These two requirements are there in addition to the fact that this is a commutative ring with unity. We further insist on n to be a power of 2, although this is not an essential property, but this makes the computation efficient. And usually such a requirement is not a burden, because we can always extend the vector by padding it with zeros. So we will also add a third requirement. Notice that this is only for efficiency in computation. So we will add the requirement that n is a power of 2. So now we are ready to define the discrete Fourier transform of a vector with n components. So let's just establish a few properties. Observation says that some omega I going from 0 to n minus 1 is 0. And this is trivial because this is a geometric series, and what this is nothing but w power n minus 1 over w minus 1. This is 1, hence this is 0, and we know that w, we are assuming that n is greater than 1. So w power 1 is not 1, and this makes it 0. And let's define a matrix A which is n cross n such that Aij, the ijth element of this is w I times j. Then the Fourier transform the discrete Fourier transform of vector A, which is A0 to an minus 1, is Fn of A equal to A and these are the entries w power 0, w power 1, w power 2, then w power 0, w square, w4 and so on. Okay. That is 0, 1, 2, 0, w square, w 4 and so on. Now, I probably need a stronger result than this. So, I will say I times j will be same as w j power n minus 1 by w j minus 1, and of course our both I and j are, note that I and j are between 0 and n minus 1, hence this is w power n power j minus 1 over w power j minus 1. This is 1 power j is 1, hence this is 0. This is not 0 because w is a primitive nth root. Hence, more generally this sum is 0. Now, using this result, we will show that there is an inverse transform. So, let us define A inverse as the ijth element of this is w I times j with a negative sign. So, this is the matrix. Notice that this is inverse because A times A inverse is sum w I. Okay, let us say this is I k th element of this I j into w minus j times k, with j going from 0 to n minus 1, which makes it j. I would have to add a coefficient 1 over n here. So, I will have 1 over n here as well. This is 1 over n w j I minus k. I minus k is a constant for a fixed I and k. As long as I and k are not equal, this quantity is other than 0, so let us consider I not equal to k. This is not equal. For j here, we will exclude 0 value, because if j is 0, then this quantity becomes 1 and this whole thing adds up to n. So, we will have to refrain from making so our j is between 1 and n minus 1. If this is not 0, this sum is 0. So, we get a 0 value. If I is equal to k, this is 0, this quantity is 1, and this whole sum is nothing but n divided by n. So, it becomes 1 if I is equal to k, which means this is the identity matrix, the ikth value of that, which is establishing the fact that indeed this is the inverse of A. Well, in case this is inverse, then we define inverse DFT of a vector A to be A inverse A, and now observe that DFT inverse, or I would simply say inverse DFT of DFT of A should be A, because this is nothing but A inverse of A, which is just A transpose, and DFT of inverse DFT of A is also transpose. Hence, we have a very simple notion. DFT or discrete Fourier transform of vector is nothing but the product A times this. Similarly, the inverse discrete Fourier transform is A inverse applied on vector A. Now, next we are going to see how to compute this efficiently. An efficient algorithm which takes the advantage of certain structure of these W's is called fast Fourier transform or just FFT. Let us suppose we have B, T is A of A, which is the Fourier transform. So, from now onwards I will just use this symbol to denote the discrete Fourier transform of vectors of size n components. So, we have Bj from here, sum W ij ai, where I goes from 0 to n minus 1. This is from this definition, we directly get this. This sum I am going to split in the middle. Now, you notice why we had assumed n to be a power of 2. I can always divide this into two parts. I will take from 0 to n by 2 minus 1. So, this is W ij a I, and I is from 0 to n by 2 minus 1 plus sum W ij. Notice that in the second half of the sum, the value of I is always greater than or equal to n by 2. So, n W power n by 2 times j term can be, the factor can be taken out. So, I will have this is n by 2 times j. So, now I can start from 0 to n by 2 minus 1, and here you have a I plus n by 2. So, I have just rewritten the second half this way. My indices I, instead of going from n by 2 to n minus 1, now will go from 0 to n by 2 minus 1. Now, W power n by 2, W power n by 2 is minus 1, because the square of this is 1, this cannot be 1, because W being a primitive root of unity. So, the only quantity that it can be is minus 1. Hence, this quantity is nothing but minus 1 power j. So, we are going to get sum I going 0 to n minus 1 W power I j a I plus minus 1 power j a I plus n by 2. This expression simplifies to this. Now, let us split this entire sum into two separate sequence. Yeah. Oh yes, you are right. This is n by 2 minus 1. N by 2 minus 1, because we are combining these. So, let us now take the two cases separately, one when j is even and the other when j is odd. So, let us say here we take j to be even. I am going to have this sum to be I going from 0 to n by 2 minus 1 w I j a I plus r. This is w power n by 2 times j. So, this is fine. This makes it a I plus n by 2. In case when j is odd, we will have this sum I going from 0 to n by 2 minus 1. So, this quantity is minus 1. We are going to write down w I j a I minus a I plus n by 2. Now, the intent is that somehow we reduce both of these into a Fourier transform of vectors of only n by 2 components. Notice that we have a sum running over n by 2 quantities each. If we define new vectors which are folded like this, the ith component is ith component of the original vector plus n by 2 plus ith component of the original vector. If I take that, similarly we do something here and try to reduce this task of computing Fourier transform of n component vector into 2 Fourier transforms of half the size, then I am going to get an efficient algorithm. Hence, let me now define 2 vectors C and D as follows. So, let us define for the sake of even j, let us define C k. You should think of j as 2k as a I a k plus a k plus n by 2. Sorry. So, this is just this k is nothing but this I here. And now, let us look at this vector. Let us define our dk as a d prime k, I would say a k minus a k plus n by 2. Sorry, yes. So, this is the initial impression that we would like to create 2 half size. In both these cases, my k runs from 0 to n by 2 minus 1. But when you talk about Fourier transform of n by 2 component vector, then we have to have a suitable primitive root of unity. So, now we need n by 2th primitive root of 1 in order to define transform of half size. So, notice that w square. So, let us observe here that w square is indeed such a root. The reason is w square power n by 2 is w power n, which is 1. Any smaller root, a smaller power, w square power j, will be w power 2j. If j is less than n by 2, then 2j is less than n, and hence it will not be 1. So, this is a primitive n by 2th root of unity. So, what we will have to do here is write the sum I going from 0 to n over 2 minus 1. Now, let me suppose j is 2p, the even case when j is 2p. I can write down ij ci, which is this quantity, as sum I going from 0 to n over 2 minus 1. Replace j by 2p, you are going to get w square I times p ci. And now this is the pth component of the Fourier transform of this vector. So, we are now successful in transforming this into a Fourier transform problem of half size. Let us now look at the second one. This sum goes from I from 0 to n by 2 minus 1. Here I would like to keep in mind that j has been replaced by 2p, hence we get this. So, keep in mind that the pth element of this Fourier transform is actually 2 pth element of the original transform. So, you have here w I 2p plus 1. Now, in this case j is supposed to be odd, I am replacing this by 2p plus 1. This is d prime I. This I can write down as sum w square I p w power I d prime I, and let us call this quantity as di. So, the sum now is well, I goes from 0 to n by 2 minus 1, w square power I p di, which is the Fourier transform of half size of vector d, and this is the pth. Notice that here j was replaced by 2p plus 1. So, when p goes to 0, j is 1, which is the first odd index. Hence, for j going from 1 to 3 to 5 and so on, our p will go from 0 to 1 to 2 and so on. So, we have again a Fourier transform of half size, and we are computing the pth quantity in this fashion. So, finally, what we get is that Fn of A P, or rather I would say 2P of this is the Fn by 2 of C, the pth value, and Fn of A 2P plus 1 component is same as Fn by 2 C, rather D, dth component, and this is the pth component of, sorry, dth vector. This is the pth component of this Fourier transform. So, all we have to do is compute the vectors C and D, compute the half size Fourier transforms, and then mesh them together, first from here, second from here, third from here, fourth from here, and so on, and now you have got the Fourier transform of A. So, now let us write down the algorithm. We have a discrete Fourier transform of size n of a vector A, and we also give the primitive root, nth primitive root. So, step 0 is if n is 1 or yes, then return A0. Notice that Fourier transform of a single component vector is itself. So, you can verify that, else now we will have to prepare to split this vector, generate those two smaller vectors, compute the Fourier transforms, and then combine them to compute the Fourier transform of the big vector. So, I will have for k from 0 to n by 2 minus 1, we will define these two vectors. Ck is ak plus a. Well, I will need one more. All right. So, I am going to have which I will show you why we need u equal to 1 here. A k plus n by 2. This was the first smaller transform. This is the vector for that, and dk. Recall that we had d prime and d. D prime was simply the difference, but in dk we will have w power k times this. So, for each component we will have different power of w, and that is what u will be. So, we will have u times ak minus ak plus n by 2, and then we will upgrade u. So, u will be times w. Hence, u is always w power k. When k was 0, u was 1 first time, subsequently it keeps on growing. Now we have prepared the two vectors. We are going to compute the two Fourier transforms. So let's call them, we have C and D. So let's call it E so this is array containing the Fourier transform of vector C dft of n by 2 C W square F is similarly so we make a recursive call for these two smaller transforms and now combine them. For combining, we will need again for k going from 0 to n by 2. Let's define B or rather we have been using just the index. I will just write down B2k is same as Ek and B2k plus 1 is Fk. Now we are done. So we can now return our vector B. This is the Fourier transform of our input A. So the complexity, I should probably put a closing brace. The main computation is generating these n components, n by 2 components of C and n by 2 components of D. Then we make recursive calls and again we generate these n components of the Fourier transform. So what we have is time complexity of computing an n component Fourier transform is some C times n plus 2 transforms of size n by 2. And the next time, of course, we will have Cn plus Cn by 2 into 2 plus 2 Tn by 4, which is same as 2Cn plus 2 power 2 Tn by 2 power 2. Hence, each time we are going to get Cn term as we go along, but this is going to reduce to simple case in only log n steps, because every time it is halving. Hence, this is order n times log n. This is the time complexity of fast Fourier transform. Now we are ready to show a very useful application of Fourier transforms, and that we will use in giving an efficient algorithm for computing product of two polynomials. So let me first define something called convolution of two vectors. Definition. So let A be A0, A1, An minus 1, and we have another vector B which is B0 through Bn minus 1. Then convolution, which I am going to define, convolution of A and B, which is A star B, is also a vector, but the size of this vector is 2n, and the ith component of this is sum of A j times B k such that j plus k is I. So, let us now expand this and see what exactly we are getting. So, notice that here my I is 0, 1 all the way to 2n minus 1, although you will notice that it will never have any case of 2n minus 1. The maximum such a thing is possible is 2n minus 2, but we will force this extra component just to keep the things of a multiple of 2 in size. In that case, we are going to define the 2n minus first component as 0. Let us just open this and see what exactly this is giving us. As long as our I is less than or equal to n minus 1. So, let us take a look at case 1 is I less than or equal to n minus 1. In that case, A0 Bi, A1 Bi minus 1 and so on will contribute. So, we will get A star B I as sum A j B I minus j, where j goes from 0 to I. This is what we will get. The other case is when I is greater than or equal to n. Now, let us take a case when say I is n plus 1, just for the sake of an example. Imagine I here n minus 1, n plus 1. So, if it is n plus 1, then A0 will not be able to contribute anything, because this is 0, maximum this can go is n minus 1, they will not contribute anything. 1 n minus 1 add up to n still does not contribute, but it will start from 2 and go up to n minus 1. So, when it is 2, it will be n minus 1, 3, n minus 2 and so on. So, when we are looking at say ith component, then I minus n minus 1 is the first index that will contribute. So, we will have A star B I equals A j B I minus j and our j starts at I minus n minus 1 and goes up to n minus 1. This is how the two cases split. In this case, the upper side does not contribute, and the lower case, the lower side does not contribute. So, this is what we have. Now, for convenience, usually splitting into two cases is a hard thing to deal with. So, we are going to show that this can be reduced into a single expression if we extend our vectors in the following fashion. And what I am going to do is define new vectors as follow. So, let us say let again we have these A0 through an minus 1, and we have B, which is B0 through Bn minus 1. Define your A prime as A0 through An minus 1 and then padded with n zeros. So, these are n of them. Similarly, define B prime as B0, Bn minus 1, 0, again these are also n zeros. So, we have defined these extended vectors of size 2 n. Then A star B, the ith component, is some A j, A prime j, B prime I minus j, and j go from 0 to I. Let us verify this. Again, we are going to just take the two cases and verify that they match with these. So, first, if my I is less than or equal to n minus 1, notice that the right hand side will be same as j equal to 0 to I aj b I minus j. The reason is that in this case all the indices are within n minus 1, because my I is at most n minus 1 and my j runs only up to I, and my I minus j is also contained, because the lowest value this can have is 0, highest is I. All these values are contained in the range 0 to n minus 1. In that range, A prime is A and B prime is B. Hence, this is indeed equal to this. So, this is actually A star B I from that case 1 expression. And if I is greater than or equal to n, then what is going to happen is that this expression j from 0 to I, A prime j, B prime I minus j. Keep in mind, every index greater than n minus 1 is 0. So, in case say we have I equal to 1, say n, my mistake, if I is n and j is 0, then we will have A prime 0, B prime n, which is 0, will not contribute anything. And this will go on until both the indices are within n minus 1. So, we will drop those terms which have contributed nothing. So, which is the first value of j when we have a non-zero contribution? Well, when this is n minus 1. If this is n minus 1, then j is I minus n minus 1. I minus n minus 1. The largest j can go is n minus 1. Beyond that, it is 0 anyway. Now, of course, both these terms are non-zero, and when they are non-zero, then A prime is A and B prime is B. So, this becomes A j B I minus j, and which is again, as we see, this is exactly the same. We are getting this. So, we have now a single expression for the convolution of the two vectors. Okay. So, now I am going to now I am ready to state a theorem, and we will prove that in the next lecture. So, now finally I am going to state a theorem which tells you how to compute the convolution of two vectors efficiently, which actually uses a Fourier transform, and the proof of that theorem we will do in the next lecture. So, the statement is that suppose we have two vectors, let A be A0 through An minus 1 and B be B0 through Bn minus 1. Okay. Then inverse Fourier transform of 2n vectors of a Fourier transform of 2n vector A prime f 2n B prime is A star B. So, let me first define. This is Fourier transform of size 2n. So, is this. Now, what is A prime? As we had done earlier, where A prime is A0 through An minus 1 padded with n zeros, and B prime is similarly so these are n zeros. And this operation, because notice that this is a vector of size 2n, so is this. So, this indicates that you multiply first component of this with the first component of this and make that as the first component of the result. Second of this, multiply them, that will be the second component. So, the encircled dot is component to component multiplication. Hence, this will again, this whole product will be a vector of size 2n, and therefore, we can compute inverse Fourier transform of such an entity, and this whole thing we will show is nothing but the convolution of the two input vectors.